with examples of solving Laplace's equation with boundary values and do some specific examples. Check to make sure that that's running.
It has rec on it, so I
Rec,
assume.
it's recording. Hi, Brian. All right. And who knows? Maybe Eli will need it this time around, too. So I want to discuss some specific examples that have to do with other geometries. Really more interesting geometries, because rectangular geometries don't occur all that frequently in electrostatics. So let me repeat the approach that you used for your homework already. Which is that what we do when we're solving Laplace's equation or any equation with boundary conditions is that you find the general form of the solution in the region of interest, right? And you write it out in its most general aspect, unless, of course, you could look at it and say, oh, I can eliminate these terms, I don't need them. But you write it out in its most general form, right? Then there are going to be coefficients on each of the terms in the most general form that you write. You find the coefficients. That's basically it, something that satisfies the boundary conditions at that point, right? I have thrown together, for your amusement, a list of approaches that you could take to solving problems. And actually the first thing that I said when I was on the previous slide is pretty much what I've got listed up there. I've actually been a little bit more specific there if you had a time-dependent situation or if you had yeah, let me leave it like that. If you had some specific situation, that what you might do is solve the homogeneous equation with 0, and then find the specific solution that works for the time-dependent boundary conditions that you might have. But we're not up to that yet. We'll come to that much later. All right. Then this is the approach that we use very frequently, and we're going to be using in this class, which is see if the solution to your differential equation can, actually this is not the approach we'll take. This is the approach that I'll show you, but once I've shown it to you a couple times, then the next approach is the one that you will take. So here, you see if you can produce a product solution, and if you can, then you have a solution. You see how you write it in its most general way, and then search for coefficients, right? This is the solution that we actually do use, right? All the time. Find a book on partial differential equations, see if the one you want to solve is a well-known equation. Actually sufficient, probably for everything that you do as an undergraduate, would be to get yourself a Schaum's, and in the 4 pages on differential equations, it'll give you all the specific forms that you need. Okay? Oops. All right, yes. The next one, right here, yeah, one word, numerical solution by integration. Or the technique that you just used. I realized that in my top 10, I'm actually not doing it in the proper order. I should have started at the least important and gone to the most important, but I wanted to save the funny for later. So, yeah, one word, numerical solution by integration. Then relaxation method, the computational method that you just used for finding the potential in this particular problem. Then, yeah, the last 3, right? Assert to your mechanics, quantum mechanics, E&M instructor, that there is no solution, and see how far that gets you. Sometimes that, in my case, if I've made the problem up myself, it might be true. But there actually is always a solution to a problem with boundary conditions. It might be 0, but there's always a solution. Question mark, yeah, who knows? And then the other one is tell your instructor who can't even count correctly, and see how far that gets you. Yes?
You're missing one.
That's worth the joke.
Okay, so I'll come back to these later. This class Don't worry, I'm not going to use PowerPoint throughout, because if I did, you'd be faced with this. Oh, God.
That was one of Professor Stoller's lectures.
I saw a row.
It really was.
No, it wasn't.
No,
It was one of my lectures.
Tell us about it.
It's only Professor Stoller's lecture that has a lot of errors. Okay.
I approve.
So, I wanted to include this in the notes this time around because I just wanted to be sure that you had the specific forms that you need for various geometries. So, if a problem naturally falls into cylindrical coordinates, you look at it and say, oh, that looks cylindrical, or polar, then you should attempt to solve the problem in cylindrical coordinates. And the Laplacian in cylindrical coordinates looks like that, right? Where rho is the distance from the center. So the terms that I'm going to use are, isn't that